So I'll be talking about topological quantum compiling. As you can see, that the references I'm showing here are rather old. So the results that I'm will be showing you are sort of also results that are more than 10 years old. But it's mainly sort of an introductory talk to the topic of topological quantum compiling, which I thought might be of interest to people outside of the immediate field of topological quantum computing. So oops. Oh, sorry, I can't move these. Oh, there it is. Okay, so here's an I don't know if I can get rid of this. Sorry. All right, so here's an outline of the talk. So I'll be basically starting by telling you about the basic criteria for quantum computing as a sort of a starting point. Then I will tell you a little bit very briefly about these phases of matter, the fractional quantum Hall states that give rise to these so-called non-Abelian anyons. I will define all these terms that I'm mentioning here that are basically the building blocks of topological quantum computing. Then with that, I will be able to tell you what I mean by topological quantum compiling, which is sort of the title of this talk. And finally, I will tell you how to actually do topological quantum computing with certain topological phases of matter that may be realizable in actual physical systems. Okay, so let's start with the basic, what is known as the DiVincenzo criteria for the implementation of a quantum computer. Sorry, I'm just trying to adjust these things here. All right, so according to this criteria, in order the criteria that is needed of a physical system that can be used as a quantum computer are as follows. We need to have well-defined scalable qubit array. So qubits are basically two-level quantum systems. And for example, it could be spin of an electron that could be up or down corresponding to the two levels of a qubit being used in state 0 or 1. Then we need to be able to initialize these qubits into some simple state, for example, polarizing all the spins in one direction corresponding to everything in the state 0, for example. Then these qubits need to have long coherence times, I should say, rather than decoherence time, meaning that these states need to stay in their qubit states long enough for us to do the computation and do the measurements. Let's see. Okay, and then we need to be able to carry out a universal set of gate operations, which consist of all single qubit gates and at least one entangling 2-qubit gate, for example, a controlled NOT gate. Finally, we need to be able to carry out single qubit measurements to interpret the results of our computation. So the main difficulties in building a quantum computer turns out to be the existence of errors in the system, mainly the third and fourth criteria. So physical systems that we use as qubits usually have very short coherence times. And also the universal set of gate operations usually carrying out the gate usually involves many errors, and this includes both systematic errors and also random errors, noise errors in the system. And these issue of errors and coherence times are large and big enough that we haven't been able to build a proper fault-tolerant quantum computer yet. So how do we address these error issues? So again, the main type of errors that we are dealing with are decoherence of qubits, which means qubits in quantum systems, quantum states of qubits interact with the environment, and the environment causes these qubit states to sort of collapse into classical states, and therefore we have some error. So this is usually like a random error. It's due to noise in the system. The second type of errors are basically imperfect implementation of the gates. So the physical system, any physical system that we pick usually has certain constraints that there are certain gates that you can maybe create exactly, but then other gates, the whole set of single qubit gates that you want to create are usually we need to approximate them. So this gate errors are it consists of both systematic errors, which is due to a sort of approximation of certain logical gates, and also it could be random that in the process of implementation of the gates, things can go wrong due to interactions with the environment. So the ways to address this the issue of errors, I guess sort of the reason that people believe that quantum computation is possible really was just due to this results from the early 90s that people showed that quantum error correcting codes are possible. And the idea of quantum error correcting codes is that you basically spread your quantum information over the global state of many entangled qubits, and therefore small interactions between individual qubits with the environment does not affect the sort of the encoded information. Another way to look at this, which to deal with errors, which also was originally proposed around the same time in the late 90s, with this idea of topological quantum computing. And there the idea is that to store quantum information in global degrees of freedom of certain phases of matter that actually are intrinsically entangled. So that's basically a property of that physical system that the state is highly, the ground states are highly entangled. So you can sort of see that there are similarities between these two approaches. Both of them are using entanglement between sort of degrees of freedom of the system. So in the first case, you can sort of think about it as a software approach to error correction when you're encoding your information in the states of other qubits in your system, whereas in the other case, you can sort of think of it as a hardware approach. You're picking a physical system that actually has this property that you can store information in it in a fault-tolerant way. And this is this hardware approach is what I will be talking about today. That's sort of the topic of this talk. Okay, so as an introduction to sort of these topological phases and these phases of matter that actually happen to be intrinsically highly entangled, let's start with fractional quantum Hall states. So the very basic idea is that you have a two-dimensional gas of electrons that these electrons are interacting with each other. You take the temperature to very sort of very low degrees, around millikelvin, and then you apply a very strong magnetic field that are the order of several Teslas perpendicular to this gas of electrons. Now, what happens is that at certain values of this magnetic field, especially when the number of the ratio of the number of electrons to the number of flux quanta happens to be a rational fraction, then these gas of electrons form a sort of a liquid, an incompressible liquid. And this incompressible liquid actually has very interesting properties. For example, as sort of a theoretical curiosity, people have shown that if you take this gas of electrons under this magnetic field and put your surface put this gas on the surface of a on a surface that is topologically non-trivial, then the ground state of this state basically depends only on the sort of the shape of the surface that you're defining it on. So, for example, for this particular case, the case where you have this filling fraction 1/3, known as Laughlin state, if you put this gas of electrons on the surface of a sphere, then the ground state is unique. But if you put the same state on the surface of a torus, then the ground state is threefold degenerate. And if you keep punching holes to your system, then the ground state degeneracy grows exponentially with the number of holes in your system. So obviously, I guess, for obvious reasons, this has not been checked experimentally, but it has been checked numerically. People have sort of shown that it's, this degeneracy actually exists numerically. Now, even possibly more interesting, these states have this property that, you know, if you introduce certain perturbations to them, for example, schematically here, I'm showing that if you add an extra electron to your system, then this electron effectively breaks apart into quasi-particles, that these quasi-particles actually carry a fraction of a charge of an electron. And even more interestingly, they have fractional statistics, which I will get into. So what I should say here is that this, I mean, obviously the electron doesn't really break apart. It's just the system behaves in a way as if you know, these quasi-particle are the sort of the fundamental charge carriers in the system, and people actually have been able to measure this fractional charge in some experiments too. Okay, it's sort of a particularly exotic version of these fractional quantum Hall states happens at filling fraction 5/2, and there's this property that, you know, if you have a number of these quasi-particles present on just a trivial surface, just on a disk, for example, then the state of this system is actually degenerate, and then the degeneracy grows exponentially with the number of quasi-particles that you're adding to the system. Furthermore, states in this degenerate Hilbert space are actually cannot be locally distinguished from each other. It's they basically are only distinguishable when you sort of measure the state of all the quasi-particles in the system. So in a sense, you can sort of think about as, you know, a system where you have a number of these quasi-particles present as a perfect quantum memory. You have a system where, by adding quasi-particles to the system, the dimensionality of the Hilbert space grows exponentially, and then all these states in this Hilbert space are protected from the environment. So it's basically a perfect quantum memory. But we're not satisfied with just having a sort of a perfect memory. We want to be able to do fault-tolerant quantum computing. So how do we actually do quantum computing with these systems? To understand that, I need to remind you of the idea of statistics of identical particles in 2 dimensions. So imagine on a 2-dimensional surface, you have a number of quasi-particles present, and you start moving these and you sort of imagine time in the 3rd dimension. Now imagine moving these particles around each other like this. Now you can see that the word lines of these particles, is this a, can I use this? Oh, well, that's okay. Oh, never mind then. Yeah, it doesn't go in. Never mind. That's okay. So you can see the sort of the word line of these particles in this 2+1 dimensional space-time trace out these braids. So exchanging 2 particles in the surface corresponds to sort of braiding the word lines of these particles around each other in this sort of 3-dimensional space-time. Now, notice that there is a difference in the shape of the braid that we get if we exchange particles in one direction versus the other direction. So if you exchange particles in a clockwise manner versus a counterclockwise manner, the shape of the braids are different. And there's no way that you can sort of smoothly deform one to the other one without you know, cutting the braids and then just, you know, moving the sort of the way that one line goes around over the other one. So they're sort of fundamentally different from each other. So the consequence of this difference is that if you exchange 2 particles twice, like this, even though the sort of the initial positions of the particles is the same as the final position of the 2 particles, we just basically start with one on the left and the other one on the right, and then we just move them twice, and then so we end up in the same place. This shape is different from exchanging 2 particles in one direction and then just bringing them back to their original position, because you can see that the shape on the right-hand side is just like having 2 lines just going on top of each other. So we can basically just move them away from each other like this. So you can see that it's the shape that involves sigma and sigma inverse is just basically equivalent to doing nothing. but that's sort of different from the shape on the left, which is basically a, if I show this braiding operation with this, sigma symbol, then sigma squared is not equal to 1. So the upshot of this picture is that in 2+1 dimensions, 2 exchanges is not equivalent to the identity. So identical particles in principle with fractional statistics can exist. Now this is something that is actually sort of a bit hard to show here, but sort of you may know that if we were not confined to 2 space dimensions, if we were in 3 space dimensions, then with the addition of time as the 4th dimension, in that case, there was a way to convert the picture on the left-hand side to the picture on the right-hand side. It's hard to imagine because you have to imagine a 4-dimensional space, but you probably know that anyway, because you know that in 3 space dimensions, the only identical particles that we have are bosons and fermions, and that the reason for that is that in 3 space dimensions, sigma squared is equivalent to 1, so sigma can be either +1 or -1, and that corresponds to, sure. Say it again. Right. So phase, exactly. So phase is one representation of these braids. Yes, exactly. So in the case of 3+1 dimensions, it's either +1 or -1, whereas in 2 dimensions, as you said, it can be a phase. Right. And in fact, so in principle, we can have this idea of fractional statistics in 2+1 dimensions. So it's actually quite interesting that when you confine yourself to lower dimensions, you have sort of richer and more interesting statistics. Whereas if you go to sort of higher dimensions, then it just becomes fairly trivial. You have either +1 or -1 only. So yeah, so for example, for this particular fractional quantum Hall state that has been observed, the Laughlin state, we know exactly what this phase is. Okay, so yeah, so and also sort of if in case you haven't heard about this, these quasi-particles, these sort of identical particles in 2 dimensions are called anyons, and anyons really just come from the fact that this phase in principle can be any phase. Not exactly any phase, it has to be a rational fraction of pi, but still, quite a large sort of number of possibilities, and that's why these particles are called anyons. Okay, so these phases actually, so in 3+1 dimensions, these sort of sigma operators, you can think of them as a representation of a permutation group, because the only thing that matters, that sort of tells you what the state of the the state of these particles are, is just their relative relation to each other. So it's it's just so the only thing that matters is just the permutation of the locations, as opposed to sort of the history of where they were. Whereas in this case, in 2+1 dimensions, the whole history of where they come actually matters. So these sigma operators in this case form a representation of what is known as braid group, and these braids basically refer to these word lines that are being moved around each other. Okay, so sort of a more exotic version of these anyons, in which that I just discussed before in the context of topological memory. If you recall, there the idea was that if you have a bunch of these anyons present, then the Hilbert space is degenerate. Now imagine that in this case, for example, just for schematic reasons, if I have 3 of these anyons, the corresponding Hilbert space is 2-dimensional. So I just write this initial state as a superposition of these two orthogonal basis vectors, psi 0 and psi 1. So I start with some initial states represented by sort of these coefficients alpha and beta. I do a braiding and I end up with a final state, which is another sort of set of coefficients. Now, if I write these vectors in just this spinor format, you can see that the initial state and the final state are related to each other by matrix. So This basically, this unitary matrix, is a representation of this braid operation. And in principle, so in this case, when you have this degenerate Hilbert space, a phase is not enough to describe this braiding process. You need a matrix to describe the braiding process. And in principle, you can imagine that, if you exchange the first two particles, you get one matrix, and if you exchange the second two particles, you get another matrix. So because these matrices don't usually just commute with each other, these sort of these braid operators are said to form a non-Abelian representation of the braid group, just because the matrices don't commute with each other. Okay, now you can imagine that, if you have many of these particles present, and if you start moving them around each other, then this whole process of braiding basically corresponds to sort of a big unitary matrix that has the same dimensions as the dimensionality of the sort of Hilbert space of your original quasi-particles. And sort of one nice property of these braid matrices is that that matrix only depends on the topology of this braiding process. So again, just to show it in the cartoon version, if you wiggle these braids if you have noise in the system, so these braids are just not nice and smooth, but they just wiggle around, as long as they have the same the same sort of braiding pattern as the original one, as long as it's the braiding pattern is topologically the same as these two cases are basically still the same braids topologically, then this matrix doesn't change. And so that's the basis for this idea of a robust quantum computation, in a sense that you can think of quantum computation also as potentially as a big unitary operator that you're applying to the state of qubits. So if there's a way that you can write this unitary operation that corresponds to your quantum computation in terms of braids, then implementing these if you implement these braids, you are basically creating this unitary operator in this robust space. So if your quantum computation is written in terms of these braids, then in principle, your computation also sort of inherits the robustness of braids. And that's the idea behind this topological quantum computing, which was originally introduced by Kitaev and then later extended by Friedman and others. All right. Okay, so but this, I guess, sort of a little introduction to the idea of topological quantum computing. Here's what we want to do. So here we're just imagining that we have we know what kind of quantum computation we want to do. We just sort of write it in terms of a circuit, in terms of single qubit gates and 2-qubit gates, and we also have potentially a topological quantum computer ready, and so we can basically braid these anyons the way that we want. So now the question is that how do we sort of convert this algorithm in terms of single qubit gates and 2-qubit gates to the language of braids? That's the sort of the question that we want to answer here. So the procedure is that we basically need to, first of all, I need to tell you how to encode qubits in terms of properties of these anyons, how to carry out single qubit gates, 2-qubit gates, and finally how to measure these qubits and then sort of extract the quantum information out of the properties of these anyons. Okay, so that's sort of basically what we will be talking about. Yeah, to just basically make a bit of more connection to reality, to just see that these anyons are a bit beyond just having mathematical, just a bit beyond just interesting, beautiful mathematical theories. There could be some connection to nature too. So here's a plot of so that two-dimensional gas of electrons that I showed you, the resistance across this two-dimensional gas as a function of magnetic field. So this is the typical experiment, like a typical fractional quantum Hall experiment, and you can see that. I think you can see my cursor. So wherever you see this, there's like a plateau that corresponds to sort of an incompressible quantum liquid that I have at a certain filling fraction, and so I mean, obviously, I'm not going to the details of this data, but this is some real data that I'm showing you here, and that this plateau really does correspond to a certain fractional quantum Hall state. So people have this filling fraction 5.5 is actually pretty robust, and the quantum Hall state that people have come up with to describe this filling fraction is what is known as the Moore-Reid state. And its excitations are these so-called Majorana particles, which you might have heard about in sort of other contexts. So these are non-Abelian anyons. But unfortunately, their sort of internal structure is not rich enough to lead to universal quantum computing. But they're still interesting, still non-Abelian anyons. But there's another filling fraction here at 12/5. You can see that it's a sort of a much smaller plateau. And there's another sort of quantum Hall state that people have proposed for this, a certain parafermion state, it's called. And the excitations in this state are these so-called Fibonacci anyons, which happen to be perhaps in some sense the simplest non-Abelian anyons that are universal for quantum computing. So and these are basically the anyons that I'll be sort of mostly talking about today. Sure. Oh, so what are the tests you mean? So I think a lot of these definitely for the loftiness state, I know that the main test is overlap. There's like a variational state, and then there's the sort of exact diagonalization of the the Hamiltonian of the system, and you look at the overlap between the two states, and the overlap is usually pretty good. So that's the way they do it. I think it's probably sort of a similar thing in this case as well. At least that's sort of the main thing. I think there are other tests too, when you can estimate the gap and then do measure the gap and sort of compare them, I think. But I think the main thing is still the overlap between like a variational state and the exact diagonalization results. Yeah. Sure. It is non-Abelian. Yeah, Majoranas are non-Abelian, but they're not universal. Yeah, I have some slides further on that I can just sort of try to visualize why it is not universal compared to Fibonacci, but they're definitely non-Abelian, but they're just not, their braid matrices are not in such a way that give you, that you can create all single qubit gates with them. No, that's not true, because with abelian anyons, you can't really do anything because you just get a global phase when you move them around each other. In this case, there are many gates that you can do. Even you can do C0 exactly even with Majorana. So it's actually, they're actually quite interesting. And if you add some non-topological processes to your system, you can do quantum computing. It's not, you can't do universal quantum computing completely topologically. If you give it some assistance away from topological phases, you can still do quantum computing with it. With abelians, you can't really do anything because you just get a global phase. You can't get a matrix with abelian anyons. Right? I think that's at least how I think about it. I mean, you need to have this sort of matrix structure to define that. Yeah. Sorry, did you have a question too? What is the criteria for it to be universal? You need to be able to carry out all single qubit gates. You need to do all the SU2 operators and at least one entangling 2-qubit gate. One thing, yeah. So in this case, you can do entangling gate, but you can't do all of SU2. That's sort of the problem. Yeah. All right. So again, just for completeness, these fractional quantum Hall states that are basically where these ideas got started. But So this Majorana particles and the Fibonacci anyons are two states within a sort of a whole hierarchy of the states that people have worked out. The mathematical theories are known, and they have interesting properties. And they just the prediction is that they should occur at this. There's a relationship between the filling fraction and this integer k, which labels these different types of anyons within this hierarchy. So Majoranas correspond to k equal to 2, and Fibonacci corresponds to k equal to 3, and k equal to 1 corresponds to abelian states, basically. Other than these fractional quantum states, there are also a whole zoo of proposals of how we can sort of potentially engineer these states. For example, there are many the references I have here are by no means exhaustive, but for example, their bosonic versions of these states have been proposed to be created in atomic and optical systems, for example. And also there are all sorts of spin models for creating these states in spin Hamiltonians. And they're also there are proposals of how to sort of create these states at the intersection of some superconductors and abelian fractional quantum Hall states. There are proposals about how to sort of create these things out of like 1D systems, and then introducing interactions between them. So there's no shortage of really interesting proposals out there, but unfortunately none of them have been realized yet. They're just all very difficult for the various reasons to be implemented experimentally. Okay, so with that, let's just sort of dive into the properties of these anyons. So these anyons are actually, in many ways, you can sort of think of them as sort of generalizations of just regular spin that we are comfortable with. So these anyons carry this, quantum number, which we call topological charge, which for these anyons, these SU2 level K anyons, can have any value between a minimum value of 0 and maximum value of K over 2. So there's a sort of a cap of how far they can be, and the minimum non-trivial charge is 1/2. And again, you can think of that as just similar to spin 1/2, for example. And similar to a spin, there are rules for fusing these anyons. So that means, if you have like a bunch of these anyons coming together, what would be the collective charge of this, combined system? And similar to the triangle rule for adding spin, there's a similar rule here. The minimum, so if you have two spins, S1 and S2, two topological charges, S1 and S2, the minimum charge is going to be S1 minus S2. And then, but there's a difference in this case. The maximum charge is not S1 plus S2. There's just, there's this sort of extra criteria so that if you have, so the total charge of your spins, total charge of your anyons can never be more than K equal to 2, no matter how many anyons you have in your system. So a notation that I'll be using throughout this talk is that I'm showing the minimum non-trivial charge of 1/2 with just these sort of colored dots, like this red dot here. And then whenever I enclose a number of these anyons with an oval and write a number next to it, it just means if I fuse them, what would be the result of that fusion? So in this case, if I have two charged 1/2 anyons, if I fuse them, I get either 0 or 1. So these are the sort of the possibilities that that I get. Sorry, say it again. So alpha is just a coefficient. So the red circles are always 1/2. If I enclose, so those two, so these two, so this is 1/2, this is 1/2. And if I enclose this oval, it just means that if I bring these two together, then they just annihilate each other. So I get charge 0. In the other case, it's just if I bring them together, then I get charge 1, the charge 1 object. Okay. So it's again very similar to spin. If you have two spin 1/2s, and then you should bring you can get total spin 0 to total spin 1. So it's very similar to that. Okay, so yeah, so two particles can have total charge 0 or 1, and actually sort of the way the way we count the dimensionality of the Hilbert space is really by just how many ways we can, fuse these particles in a sort of a certain way. So if you have two particles, two charged 1/2 particles, there are two ways to two outcomes basically for the fusion. So the corresponding Hilbert space is two-dimensional. So any state that I want to define in this basis is basically just going to be a superposition of, oval 0 and oval 1, for example. And likewise, if I have three anyons, if I define my order of fusion such that I first fuse the first two particles and then add the third particles, then you can see that there are three different possibilities for how these things can be fused. So the corresponding Hilbert space is three-dimensional, and you can sort of show that as you add more particles to your system, the dimensionality of the Hilbert space grows exponentially. So it's basically the sort of what is known as quantum dimension, which is the rate of change of Hilbert space as you add more particles to your system to the number of particles. That's how the Hilbert space grows. So again, for the case of Abelian anyons where k is equal to 1, you can see that the dimensionality of the Hilbert space doesn't change because it's just no matter how many particles you have in your system, you only have a single state because it's Abelian. So d is always 1. Whereas for Majoranas, when k is equal to 2, then the dimensionality of the Hilbert space grows as square root of 2. You might know this from your sort of other exposures to the Majorana particles. In the case of Fibonacci anyons, this dimensionality is actually the golden ratio. And the reason for that is that if you sort of add, that might actually be a bit confusing because you might think that, how could the dimensionality, actually be an irrational number? But the way it works is that, these numbers are just sort of, asymptotically as you add like infinite number of particles to your system, how the, what is the sort of the rate of growth of your Hilbert space. So in the case of Fibonacci anyons, as you can guess from the Fibonacci, if you have more and more particles added to your system, the dimensionality of the Hilbert space grows as Fibonacci numbers. So asymptotically, the sort of the rate of change is the golden ratio. Okay, so I guess it gets back to the sort of the idea of doing quantum computing with these guys. So it has been shown that among all these sort of possibilities of anyons, if k is equal to 3 or k is greater than 4, then those anyons can be used for universal quantum computing. Sure. Yeah. Which is what? Well, okay, so sort of you can sort of think about, the dimension when you have just imagine you have just spins, just spin 1/2. If you sort of keep adding them to your system, how does the dimensionality of Hilbert space grows? It's 2 to the n. Right? It's similar. It's just a sort of an extension of that, but just for these different types of particles. Yeah. Okay. All right. So with this information, now we can actually go to the idea of encoding the qubits. So I define qubits in this particular way with 4 anyons in a way, and I define this particular order of fusion that I fuse the first 2 particles and the second 2 particles, and I make sure that the total charge of the whole of all 4 of them is actually always 0. So if the total charge of the first 2 particles or the second 2 particles is 0, then the qubit is in the logical state 0. And if the total charge of these the first 2 and the second 2 are both 1, then the qubit is in the state 1, logical 1. Now, if you sort of look at all the possibilities of fusing 4 anyons, you can see that it's basically the space is 6-dimensional, so you have 4 other states. So all these other states that correspond to having total charge other than 0, these are sort of, we call them non-computational states. So when we do quantum computation, we want to make sure that we stay in this space of, in this qubit space. So any potential, leakages from this non-computational states is a certain error that we have to try to avoid. Yeah. Okay. So with that, I guess, I mean, going back to this, algorithm and how we want to sort of convert this to a sort of braids. I guess I told you the first step, and that's how we can encode the qubits into the properties of these anyons. Now, braid matrices. So again, as part of the properties of these sort of anyon models, we can calculate that, if you're in this particular basis and if we exchange the first two particles, what phases we get. And in the same basis, if we exchange to the second two particles, then what kind of matrix we get for that. And it turns out that, again, in this basis, there's really no real difference between the first two particles and the second two particles. So exchanging 1 and 2 is the same thing as exchanging 3 and 4. So we don't have to worry about that. We don't have to talk about that. So we will do all our computation just with these two, with braiding these 3 particles, 1 and 2 and 2 and 3. Again, I mean, the details here don't matter. It's just, I'm just putting them there for you to know that these are basically known. Now to do, now if you're, I guess with this information, if you're given a braid, then you can sort of find out what is the corresponding unitary operation to that. You can just, divide it into single braids, sigma 1, sigma 2, and their inverses. You multiply them by each other, and that gives you the matrix that corresponds to this braid. Okay, now to show you, I guess, tell you a bit, maybe try to sort of visualize this idea of, universality for different types of anyons. Let me just remind you quickly of this notation where you can sort of show these, you can represent these various SU2 operations, single qubit operations, as dots in this sort of solid sphere of radius 2 pi. So each dot, depending sort of the length of this vector, basically gives you the sort of the rotation and the amount of rotation, and the direction of this vector tells you the direction of rotation. So for example, so I mean, I guess, for example, if you wanted a 2 pi rotation around the z-axis, it would have been just the top here. Or if you needed sort of pi rotation around the x-axis, it would be a dot around here. So that's how you sort of represent it in this sphere. So the braid matrices for say Fibonacci anyons, for example, correspond to these 4 dots. So I have for purely sort of technical reasons, I'm showing you sigma squared as opposed to sigma. So it just corresponds to having 2 anyons and then going one completely around the other one and coming back, instead of just showing an exchange. But I could have as well just show you exchange. So it's just not really that different here. So here are the 4 dots that correspond to sigma 1 squared, sigma 2 squared, and their inverses. So yeah, so I guess sort of the purpose of this thing is that, if we keep adding to the length, so here I'm showing you just single sort of braid operations. If I add to this length of the braid, the idea is that, if these are sort of universal for quantum computing, then I should be able to fill the sphere completely. I should just basically have, all the fill it, because each cell corresponds to a unitary operation. And if I want all the unitary operations, I have to sort of have the full solid sphere. So here I'm showing you 4 different spheres corresponding to 4 different anyon models. The Majorana, Fibonacci, k equal to 5, and k equal to 4. And the claim is that the first 2, k equal to 2 and k equal to 4, are non-universal, and 3 and 5 are universal. So here in the bottom, I'm showing you the length of the braid. So here is just 4 dots for each of these spheres, for braids of length 1. If I have 2 braids, then I have more possibilities, a bit less than 2 to the 4, because some of them sort of cancel each other. But so you can sort of see that, the number of dots in this sphere grows. And if I keep adding to the length of this braid, you can see that, you can sort of easily see that in the case of the universal ones, the sphere fills up pretty quickly, whereas in the case of the non-universal ones, they keep sort of repeating. They just, if you add the length of braid, they just the same existing dots are repeated, and you just don't have extra ones. So that's one way to sort of visualize that, why these two are universal and these two are non-universal. Sure. Oh, in this case, it's 9. What do I mean by what? Oh, number of operations. So here, I mean, see, I have like 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, maybe I have more than 11. Yeah, that's sort of a good way to have the speaker check her data. But yeah, order of magnitude is right. Yeah, sure. Similar reason to k equal to 2. It's just the way the angles of rotations are defined are such that they just repeat themselves. I think as far as I know, only 2 and 4 are non-universal. The rest are all universal. Yeah. Okay. All right. So so here's an example of a single qubit gate. It's just a Hadamard gate for anyons of k equal to 5. I think this is about 50 operations, and it approximates a Hadamard gate to the with an accuracy of 10 to the -6. And so in principle, it's actually pretty easy to find these anyons because this just involves multiplying 2 by 2 matrices. So you can do like a brute force search for each gate that you want. And if you want even more accuracy, you can always use the Solvay-Kitaev algorithm to just systematically increase the accuracy of your gates. And I mean, it's even more efficient algorithms people have found in recent years to sort of show, or maybe not so recent anymore, to sort of find these gates in an accurate way. And also, I mean, I should say that, there's this general rule that as long as you're braiding sort of within an oval, in this case, in the case of single qubit gates, all the braiding is done within this overall charge of the qubit. This overall charge does not change. So as long as these anyons are not coming out of this qubit, then the overall charge doesn't change. So with single qubit gates, you never have to worry about leakage errors. You're always in the qubit space, and finding them is relatively easy. As I said, you can just carry out a brute force search just by 2 by 2 matrices. So single qubit gates are easy, and so yeah, I can replace these single qubit gates by the corresponding braids. 2 qubit gates are more complicated, partly because in order to entangle the 2 qubits, you need to pull some anyons from one qubit and braid them around anyons of the other qubit. And in principle, that's, if you don't sort of control the process, these overall charges can change. So you have to worry about when you're doing your braiding, you have to sort of do it in such a way to make sure that you go back to the computational space here. Furthermore, here you have many more anyons. So in this case, it's I think the Hilbert space is I think these are SU2 level. Yeah, okay, sorry. I'm having anything. So it's for 8 anyons, it's going to be SU14. So you have it's a 14 by 14 matrices, so you have 195 free parameters. So it's actually much harder to do numerical brute force search for these gates. So that's another reason that these are difficult. So so I guess in the remainder of the time, I'll just give you some strategies of how to create these 2 qubit gates. And the basic idea in all of them is that you sort of try to map this hard problem of 2 qubit gate somehow to the easy problem of single qubit gate that you know how to solve, and then basically get over this hardness that way. So instead of braiding 8 anyons, you just reduce it to braiding only 3 anyons at a time, and that sort of solves the problem. All right, so yeah, so the main sort of one of the sort of easier constructions is this one. So the aim is we're aiming at building a controlled 2 qubit gate. So I have a control qubit and a target qubit, and as you know, the target qubit is affected only when the control qubit is in state 0. In the state 1, and nothing happens if it's in the state 0. So So yeah, so for example, it's a controlled phase gate. As you can see that, so I mean, I get the phase only when the control qubit is in the state 1, and also the target qubit is in the state 1. So to build this, so the key idea here is that instead of braiding a single anion, I pick a pair of anions from the control qubit and weave that around particles in the target qubit like this. The reason for this this choice is that if this pair of particles, I call it control pair, if this is in the state 0, then as far as topological charge is concerned, this is like a sort of vacuum state. So when the control qubit is in the state 0, it's really like, I'm braiding a charge 0 particle, so it's just like braiding nothing. So when the control qubit is in the state 0, I can just basically get rid of this thing. So you can see that by just using this simple trick, I've already created a controlled something gate. If the control qubit is in the state 0, which is this block, I just get an identity. Now, so the target qubit is only affected when the control qubit is in the state 1, which is this block. Also, because this is a unitary, this is a 4x4 matrix out of a unitary. Once I have an exact identity here, I know that these rows are also exactly 0. So we can sort of play this game again now with the target qubit, and we can say that now we move this control pair around pairs of particles in the target qubit, and you can see that again we can use the same argument and say now if the target qubit is in the state 0, then I can just get rid of them like this, and then I can just stretch this weave into identity. So that again, it looks like I have done nothing. So again, for this, the case when the target qubit is in the state 0, I get an exact 1. So the only non-trivial case is when I have, both control and target in the state 1. And in the case of Fibonacci's, it turns out that 2 anions with total charge sort of 1/2. So the total charge 1 is basically has the same braiding properties as just a single anion with charge 1/2. So when both of these guys are in the state 1, I can sort of replace them with single anions like this. And now you can see that this basically braid looks like just a a single qubit gate on this sort of big qubit. The only thing I need to do is to just get the right braiding pattern here, that if I sort of repeat it by weaving a pair of anions around pairs of anions, just gives me this matrix. And this braiding pattern I can sort of figure out. For example, in this case, I wanted to create a negative controlled Z gate. So I find a braiding pattern that in this spaces for this qubit corresponds to just negative identity. And now if I follow this braiding pattern with my pairs of particles going around pairs of particles, this leads to this matrix in which, again, the only approximation is just this -1, and then all the elements of the matrix are exact, which is sort of as close as we have come so far to creating a sort of an exact 2-qubit gate with braids. Yeah, so I guess I'm almost, done with time. I just basically just briefly mentioned that, this method can be generalized so the thing that I described to you was just for Fibonacci anions. For general K, you can't do this exact thing because in the case of anions, I guess in the case of other anions, you have sort of more fusion possibilities when you have, these 8 anions. So you can't really reduce it easily to sort of a single qubit gate. But there are ways to do that, and sort of one way to do that is just to sort of break the braid into sort of 3 sections. And again, each of these sections can be reduced to a single qubit gate, and then sort of you can solve the problem that way. And so, yeah, this is an example of, again, a negative controlled Z gate for K equal to 5, for example. Yeah, and just, in terms of, I guess, I mean, those of us who've played with these braids have always been craving for, finding exact braids. And as far as I know, there hasn't really been any sort of exact entangling 2-qubit gate for any K, really, for any gate. Some parts of it you can do exactly. So for example, it turns out that, for these values of K, you can do the middle section exactly, but the sort of the first the first and last sections we never found, and I don't know if anybody else has found that. So the question of finding exact entangling 2-qubit gates for these anyons, I think, is still open. Yeah, so now I guess we know how to do 2-qubit gates, so I can sort of complete this picture. Yeah, so and I'm sort of basically done. I guess to summarize, I told you how to briefly, how to encode and qubits in terms of properties of these anyons, in terms of topological charge, how to carry out single qubit gates and 2-qubit gates. I didn't mention anything about sort of measurements, but at the end of this process, you can sort of imagine that you can sort of bring these anyons together and then sort of measure the charge out of that, and then interpret the results of your computation out of that. So with that, thanks for your attention.